So welcome everyone. Thank you so much for joining us for our Global Future Alliance International webinar series. This is our first presentation of the semester. And again, thanks so much for coming. I know this can be a very busy time of year with back to school. So I am delighted to introduce our guest speaker, Dr. Wei Liao. Dr. Liao, a registered professional engineer, is a professor and director of the Anaerobic Digestion Research and Education Center in the Department of Biosystems and Agricultural Engineering at Michigan State University. He obtained his bachelor and master's degrees from Jiangnan University in China and his PhD from Washington State University. Dr. Liao's research and teaching focus on renewable energy and environmental sustainability, and he is leading an active research program on developing integrated systems to utilize organic residues for energy and chemical production. Current research areas in his group are integrated farm-based biorefining, solar bio-based solutions to convert organic wastes and wastewater into energy and clean water, and one carbon platform for food, fuel, and chemical production. His group is also carrying out extensive research projects in Latin America, Europe, Africa, and Asia. So please join me in welcoming Wei.
Sure, yeah, topics, as Amy just mentioned, I'm going to focus on the securing agriculture in a changing climate. Very much focus on this food, energy, and water for energy and food. A little bit more focus on food and on the water energies, the sections for the food production. Again, my name is Wei Liao. I'm the director at MSU. Then we have the center. We'll talk a little bit about center. We have 20 plus faculty members affiliated centers, mainly on the research orientation from engineering and all the way to School of Social Science. And we do have a social economics on board because later on you'll see, and social economic aspects is very, very important for any solutions we want to develop for rural communities. So. And just to give a few facts why we are here and to talk about this, solutions and integrated solutions, not like just for the crop production or for some other energy production as individual cases. We have to kind of consider them as whole, as a system to develop the solutions. So first things like again, a lot of debate on this whole global the climate stuff, but this is a reality. Temperature is reality of put climate change aside, right? That's kind of very scientific data out of there, and can see this global average temperature change, and scientifically we know, and maize, soybean, all those productions, and from different studies, right? Temperature influence on them, and that's just kind of give us see the whole severe. And on the other end, our population still increase. 8 billion people and still keep increasing, depends on rate, depends on continent. And then the temperature keep increasing. This kind of going opposite directions. We have to address those issues. This just kind of give you a little bit overview on the temperature and then the impacts on our crop systems. And then let's look at the current situation we run into food, energy, water challenges. And we summarize this current the food, water, energy systems this globally, and each country pretty much follow. And energy production from fossil and all those kind of things, and use some water because no matter if fracking or doing all those kind of stuff, you need quite a bit of water there. And then the energy, water, they link together. Of course, water for energy, we'll consider a little bit hydropower, particularly like in Nepal, this is Southeast Asia, and a lot of countries rely on the kind of hydropower. And food production, of course, is kind of the entire agriculture is kind of dedicated for the food production. Again, need some water, of course, need energy, particularly modern agriculture and all those machinery and all those kind of stuff. And at this moment, all three sectors release, greenhouse gases because water, if you think about irrigation, will withdraw no matter from the river or from the groundwater. And this is a current situation. And this is one of the reasons, actually, the temperature, because within all those, the modern technology applied on this energy, food, and water, we actually, the increase, greenhouse gas emissions, particularly this entire, industry rely on this fossil-based, the energy source, those kind of things. And then some numbers, I think many of us know that 3 to 4%, crop yield increase they required to satisfy this population increase and energy needs. 550 extra joules is a huge number. And again, 1.2 billion people still need clean water. And I'm traveling around the world, and last year in the South Africa, then they really kind of realize how severe, how critical water issues. Just look at that continent, right? Southern part in the Botswana, that areas. There could be some conflicts between those countries and just fighting for water resources. And then, of course, with this many people on this planet and with the generation, 40 billion 40 billion tons of carbon dioxide every year we emit into in atmospheres, and then our the carbon dioxide concentration runs close to 500 ppm in the air. And then, of course, all those kind of wastewater and agriculture residue. Agriculture residues actually have a twofold. One is like, okay, there's kind of the consider them as waste streams, residue streams, but at the same time, this is what this talk we're going to focus on. And they carry carbohydrates. They have all those energy content. How could we efficiently use that and to turn them into some of the resources? And that's very important for the agriculture. And of course, the food waste, 1.3 billion tons of food waste produced every year. Those are just kind of numbers of facts. Okay, let's kind of come back to our agriculture sectors. Look at the animal industry. Look at our crop industry. It's two biggest the operations in look at entire agriculture. And this is traditional. We just want to show you one of that we can do all kinds of dairy, cattle, chicken, and all those industry. But this is dairy industry. And this is kind of give you overviews the water demand for the animal industry for different the animals, cattle, beef. But I want to emphasize just using the dairy farm, dairy cattle as an example. And then again, energy demand, the water demand, that's just numbers of the published number on that. But if you look at just one cattle, the one the dairy cattle, and look at the carbons from of the feedstock like corn, soybean, all those the stuff we're feeding there. And if you look at the carbon flow, right, only 35% of that carbon ends up in the milk. And of course, 20 to 30% of carbons are used for the metabolisms, energy, and they need kind of they do all other the respirations, rooming activity, those things. Another 45% of carbons ends up in manure. 35 to 45%. It just depends on the different operation. Then look at other nutrient components, nitrogen, phosphorus, potassium. Even less, 13 to 20% of them ends up in the milk, and the majority of them ends up in the manure. So this is why people always talk about it. This I always have some argument with the like impossible meat, all those artificial the meat producers, fermentative process. I'm not against them. Yeah, there's the direction, right? We call it plant-based protein or something like that. It's very good, the approach. However, the old concept we talk about the animal industry is not environmentally sustainable. It's because built up on the current boundary. Boundaries right now is like a feed animal coming in, and end products is your meat or milk, all those products. Manure is out of boundary. Manure is like say, okay, you guys can use that for as a fertilizer, but it's not for the animal production. Look at these pictures. Of course, if you don't include manure in there, the animal industry is never going to be sustainable because of they only use a small portion of such expensive. Once we talk about expensive, it's not about a cost. It's about the environment. Yeah, the environmental cost too. All those the water we use for the crop, right? So this is one thing we have to rethink our agriculture. Sometimes we need to redraw our boundary for individual sectors, and then we can look at the overall pictures. Can we do more to improve efficiency and at the same time increase the sustainability? So that's one example. The other one is again the crop, the industry. And a crop industry, most important thing is water. And this is why I just put the water use efficiency. I'm not talking about yield here. There's a lot of genetic technologies and breeding. And in the past 6 or 7 decades, really kind of take the yields. We actually did pretty successful the effort on that part. But water actually is not changed too much, particularly in the United States. Most of our, the cropping systems, we call that, tile drainage. Literally, it's like tile drainage is a nice name for those kind of irrigation. In plant world, it's a flooding field kind of, the do those kind of irrigation. European countries better than ours. They do the dripping irrigations. But overall, water use efficiency, almost like in same, category. And everybody knows 1/3 of the fresh water we draw globally, particularly in the United States, for the agriculture. The other 1/3 is for energy. And those waters very much is one-time use. And after flooding and ends up into some storage, then eventually going back, the river or going to groundwater, all those places. Can we further do the water sequestration to make those water withdrawal more efficient, like a multi-purpose after the irrigation? Can we use this water, or even much bigger picture? Can we link the power industry water and the irrigation water together? That's some of the research we're doing for that case. But this is two cases. If you look at overall water use efficiency, right, per cubic meter water use. This is for the corn production in the United States and around the world, and soybean production is quite a bit of water. If you say a cubic meter of water is only like 2 kilograms, the products, right? Think about the water amount is huge. So with that being said, so we have to really think about this, the conventional, but not conventional, the current, our water and food systems, what we can do, and to really improve the systems into a more sustainable, the more sustainable systems, not only one, the solutions. So this is kind of the MSU with all the collaboration, including our, the colleagues from Nepal, from around the world. We think and we should do all the technology. It's not only just we're doing, a lot of people around the world, including our friends in University of Maryland, doing those things too. Energy, we need including more of those circular based. Everybody knows circular economies. Circular economy is not only just like for one process or another process, it's a system concept. So you really need to kind of do the big circle, small circle. You really need to circle everything, the up. And for this case, it's really kind of food, energy, water, food. Those circle need a kind of a back and forth. It's not like this current system, very simple, the one way, or, the kind of simple, the pathway is more complicated on that. Eventually, those things are interconnected and then can help each other. For example, agriculture. Agriculture in our, perspectives, our vision, is going to be big, portion for future energy, generation. No matter, there's a lot of debate, particularly DC around the country is talk about a photo agrivoltaic and some other things. Those are good questions, need to be answered, and we're working on them. And then fooding, the agriculture industry, we're kind of, I'm not saying to replace our energy industry, but we'll make a major contribution to them. And then water use. Again, water use is not only just for food production, for our human consumptions, and need a link to by the other, like irrigation, energy. The water should circle them up. And then all those processes we're developing really kind of, the carbon efficiency is a very important piece. So eventually really change each individual, the component in the systems, makes them a, carbon neutral, even carbon negative, the systems. Then we can consider the circular economy or circular systems to achieve this zero discharge, zero emission, systems, more sustainable, way. So this is our dream. I'm going to kind of give you a couple of examples and research what we're doing to achieve this, overall, or, the overarching goals there. So just again, those are the facts. Just can give you a little bit, the background on our ADRAC, MSU ADRAC, and the historic. Take a minute too, and give us 3 examples. Actually, one of them are 2. The number one is like anaerobic digestion, next generation anaerobic digestion. How could we increase the carbon efficiency, enhance this, the actual methane and all those, the waste handling efficiency. And the one common platform is very much just on the nutrient recovery side. How could you use the algae and algae-related technology? This is just an example. We have more other things because time limitation, it cannot expand to everything. And I'll give you some examples of system equation. This is just two individual systems. We're trying to put them together, and some efforts we're doing in Europe and other places, and back to the States. You can see some of the real palette type of the systems that we're trying to put together. And of course, towards the end, we currently have a $100 million projects going on, and we just finished our new data farm. I'll show you some of our climate smart. We call that climate smart animal operation, but the eventual goal is carbon neutral animal protein production. We're not there yet. We just kind of finished construction last month, and we're just moving. Show you some picture there. So MSU Agile, we start 2009 with a group of engineers, agriculture engineers start that, and very much just think about look at how and agriculture residue utilization. So how could you develop different solutions and to satisfy academic research need and also build a bridges, link academic industries. So this is after the 16 years development, we built our center, this MSU Southern Campus, and then we kind of our very first plug flow reactors 15 years ago. We got a little bit state funding support, and after that we built the CSTR. Actually, Fami's master research pretty much on that CSTR reactor, the 2013. And then we actually built other facilities based on ADRAC and on campus. MSU campus, just like University of Maryland is pretty big, and we have our own power plant, 100 megawatt. So we built our the algo systems to study, pilot study for carbon sequestration, utilization. Then we built another facility. East Lansing is like a college town. 50% of the population is from MSU. So we own 40% of our wastewater treatment plant. So we put our wastewater systems on the wastewater treatment facility. Again, system integration, solar and biological, non-biological system together. So right now, they actually start from 2024, we upgrading our digestion system because our dairy farms, new dairy farm increased from 250 cow to 650, and doing all kinds of research. So we are adding the RNG capacity to the new facility, renewable natural gas production. You'll see some of the pictures later on. So then the entire Agile, we're doing three things. One is like a fundamental and applied research, all those microbiology and some of the basic the chemical electrical system developed, and then can doing some pilots. Second part is education. We teach quite a bit of courses and give a lot of tours. And not only just in the school and a lot of the legislation bodies. We host like next in 2 weeks. I'm going to host another workshop for state legislation, both senators and representatives, and also we do a lot of things for the federal governments, and including legislation body. A couple of senators and Congress congressmen come to us, ask questions regarding this the annual digestion and some other things like e-ring, those things. Sad story about e-rings because EPA is putting them out. And before we put quite a bit of efforts and helping EPA, X-Star program, doing all kinds of things. So ADRAC, and then the third one is actually technology transfers. It's very important, particularly as engineering majors, to understand stakeholders' perspectives and know what they need and what we can deliver. So annual based, last year we had 170 service contracts from those big company, British Petroleum and Chevron, all the way to some SBAR, or small companies, and locally. And then we also do a lot of things around the world. And we have German projects going on, and then the SPAM and some other European the projects going on here. So we're trying to kind of really provide the platform to do those, to open to all kinds of collaborations and to do research. We are interested. We have mutual interest on that. So that's kind of our the three, the missions for this center. So build up on that. You will see some of the examples in coming slides. So that's kind of a dynamic the flowcharts. Again, engineers. So most of the chemists they are engineers on board. They like a flow chart, and it's like the social scientists, they love to see those things too. See all those flow chart, how quickly they can take components into the rural development model, or like a they call the agent-based model, those kind of stuff. Yeah, also help them too. So we keep the modifying this flow chart and really kind of trying to address this organic residue. We consider carbon dioxide, and eventually carbon dioxide will become a feedstock. Right now, we consider that as a waste streams. But if you look at right now, the off-taker and uptaker, right, we are really kind of moving into the uptake technologies, not just off-take. I don't know that we need to expand a bit terminology. I think most of the ours. We just quickly talk about off-take and uptaker. Off-taker is just like we already kind of emit from those fossil-based carbon, all those things. We're trying to reduce that emission. We call that off-take. If any kind of percentage we can reduce from current the system called offtake, but offtake is not enough. If you look at the trends, this temperature movement and carbon dioxide concentration in the atmospheres, and in very short time period, few years for that cases, we have to do things for uptake. Means that those carbon dioxide already existing in the atmosphere, so we need to figure out a way to take them out. That's a really challenging job. You later on you see why we do the algae, all those kind of stuffs, right? And we have to develop. We have to be ready. Scientific community have to be ready. Once industry, like if you look at the current, I'm traveling around the world this past summers in Europe, right? All this extreme heat during summertime. The Spain and Italy. Italy was, I mean, northern part of Italy. It's supposed not that hot before I went there. The temperature is like 40 degrees Celsius. It's like 100, 110 or something like that. It's even kind of good Alps. The Alps is pretty warm there too. It's really kind of unusual. So those kind of stuff we're trying to working on. This flow chart actually we're kind of to address that. In flue gas is offtake, carbon dioxide in air is uptake. So we do develop the things in that. Again, we can give you a little bit details in coming slides. We use the anaerobic digestion, not only just for the carbon sequestration. Anaerobic digestion has a reputation for the carbon capturing. But we really want to can tune out anaerobic digestion technology in carbon and nutrient recovery. And at MSU, we do work with different agencies very intensively doing ammonia recovery. It's not for fertilizer. We consider ammonia as a hydrogen transition, compounds to move into the hydrogen economy. So, and that's something we talk later on. And then, of course, water reclamation. We design all kinds of the biology because time limitation. I'm not in kind of expand our biological systems. Right now, really, we're moving to phage with the phage to control the biological process to really improve the efficiency and to manipulate. It's not a genetic modification because genetic modification is a lot of issues on the kind of environment, the processes. And we use the existing phage in the systems with the advanced microbiology right now we have, all those the identification, even mRNA technologies, we can move to that stage. We can control the phage, and we use phage to control the microbials and do all those. Phage is a lot of research viruses, right? Feed and transport. We really want to move them to the next stage with the phage as a process control factor to do all those things. So that kind of could be very in-depth. We can kind of, if some of you're interested, we can further discuss that. We do have a couple of fun projects on the piece. And the engine part, we do work with a lot of the engine company doing those kind of things. And then we were kind of focused on algae piece. So let's kind of take a look first, the piece. I just extract something out of this flow chart, the anaerobic digestion piece we can focus on. And the challenge, anaerobic digestion technology, everybody's talking about. And then actually getting to the real implementation, particularly in state Michigan, we get a huge resistance because of water issue. And we are in the Great Lakes, so a lot of people, including me, want to protect the lakes, right? And once get those kind of K4 operations, put all those the digests, particularly community-based digests together, right? The size getting bigger and bigger. So this digestate handling and also carbon efficiency becomes very critical issues. So this is kind of a current situation, and we look at carbon side. And carbon conversion efficiency and 40, 50, 70% of total organic carbon is turned into the gaseous compounds, methane and carbon dioxide. And then if you look at the methane content, is literally is only 35, 50%. So most carbon, a lot of carbon being converted into carbon dioxide. Is there any way Because once increase carbon efficiency means, so we can scale down anaerobic digestion technologies. If we look at how, the systems currently in digestion technologies register on actually offer large scale systems. So we want to change that, kind of technology or, that implementation. So innovation solutions needed really can focus on this carbon conversion efficient matter. So I give you examples what we're doing here. So because all this, I'm not going to focus on electrochemical things. Actually, there's many companies in the United States around the world, and they can do pretty efficient, develop the pretty efficient methods to turn carbon dioxide in format. Format is just one single carbon acid, and use a tiny little, use not a tiny little, use a bit smaller energy amount. We can turn that very efficiently, conversion efficient, like we talk about Faraday efficiency, those electrochemical terms and a 90% efficient turning into format. And then back then, we talked to our chemical engineers doing this process. What we can do the format. Format is not very efficient, acid. It's not like acetic acid. Acetic acid contains a lot of content, a lot of energy can be used for all kinds of a biology process. This one is a very low energy level and then also toxic. Everybody knows the formic acid. Sometimes we use for cleaning things, right? And then we look at anaerobic digestion. We really look into the fundamental of the metabolic pathways. And if you look at, there are two big groups in anaerobic digestion. One is bacteria, the other archaea. Communication between bacteria and archaea is not a whole lot of ways. Only like two or three pathways. One is from proton transfer energy between these two groups. The other one is actually carbon. Carbon is based on the carbon dioxide. Actually, format plays very important role as a bridge to kind of make a carbon transfer from the hydrolysis stage in the front end, exogenous into this mesogenous stage to produce methane. If we can enhance format, by principle, we are able to improve the carbon efficiency. Carbon efficiency when talk about methane conversion efficiency from all those organic carbon matter. So that's kind of the rationale behind of that. We want to kind of really look at the format impact on this, the anaerobic digestion systems. So then we kind of start all those, the things we start from 16R right now. So very much we're moving to this the shotgun. That's quite cheap right now. So the costs keep dropping, and but we see the shotgun gene moving in. We mainly focus on. We want to understand a little bit more other things besides bacteria or the archaea. We want to understand some eukaryotes in there and some of the like right now we do the shotgun genes 0.2%. The communities in these anaerobic digestions are the virus, very tiny little amount, but those viruses play sometimes very critical roles, like bacillus phages or some other phages. Actually, they actually manage the population in the system. So that's something extent we talk about later on. The future, if some interesting from colleagues at University of Maryland, we can talk about those. And format identification is a little bit tricky, and you can use the HPLC, those waste matter, but our the digestion process is very complicated matrix. There's a lot of other chemical that influence that, so we have to use a little bit advanced tools, NMR, to kind of get that format identified. So this NMR we are using to do those kind of the analysis. Very clear once we run this format enhance digestion, and very much is archaea because it boosts. By principle, we know format in that it can boost this pathways. You can see this with a pretty high format concentration, 1 gram per liter, we add into that. You can see this archaea communities significantly increased. It's not a little bit. Once we talk about the communities, we look at least a 50% increase. We consider that significant. And everybody's some microbiologists here know the 10-20% that could be just an error range or just case by case difference. So this is a very clear from community analysis. We see this peak of the archaea in the systems. And then kind of, so we look at it, we need to see the performance. Most of us know in that areas, during this, very complex community systems, there are a lot of, microbials are silent microbials. They are not, they're acting at any time. This is why we move into mRNA to really understand at any given time what kind of groups are working on that digestion. And so at this moment, we still running the traditional 16R, those combination analysis. So we still need using the performance, chemical performance to verify those microbials, enhanced microbials, they are really functioning to do their job. So you can see this carbon efficiency control AD with the formatting enhanced AD, and there's a 70% more methane production. So this is something actually a couple of companies very interested, including British Petroleum, and we're trying to really implement. This is lab skills, 1 liter. It's a little bit on the fundamental side, continuous reactors, and we're scaling up, and including Lindy, and very much focus on these methanations using different ways. This format is one. We have some other, additives to kind of enhance that. It's very promising ways, particularly like Lindy's projects we're working on. We want to build up on that. We really want to change this current anaerobic digestion technology from like methane composition 60-70%, lift that up to the 80 to 90. 90 is kind of Lindy's the goal. We are confident we probably can reach the 80%. So once get that level, what that means in the United States, current the common sense is like you have to have like a 1,000 cattle equivalent the waste streams. You can build a digester and just trying to make ends meet. Once you increase the carbon efficiency, 20-30% carbon efficiency increase, that means you have more energy coming out of the systems, no matter what you use for the electricity or RNG. And you really can scale down from 1,000, the cattle, so dropping down to probably 700 cattle equivalent. You actually really expand. If you look at the entire, the U.S. agriculture, 90% of them still come for small and medium. Of course, definition a little bit different in the United States than European or in the other rest of the world. But 700 cattle equivalent will consider medium small farms, and you really increase the spectrum to be actually able to be to use those kind of technology. Okay, this is just one of them, just a quick example. And the second one is really kind of this carbon dioxide piece. And again, we use algae culture, but algae culture, everybody knows photosynthesis efficiency is pretty low. So this, again, we work with our chemical engineering faculty member, combine those things together. And this Department of Energy fund the project and really kind of do the culture first. And we look at the microbial, look at the algae composition. We're trying to extract the efficient, components, develop, some value-added products or, develop intermediate products to enhance carbon sequestration. This is why I kind of focus on this amino acid salt absorption. Actually, amino acids coming out from the protein in the algae. There are two types of algal cultivation. One is on the power plant, flue gas. We consider those algal biomass are very clean and need to go for food because protein rich. We feed animal, all those kind of stuff. And then the algae cultured on the waste streams, for example, digestate or wastewater. You pretty hard to turn them into, even though we can do that. We can clean them up enough to make the food, but there's still a lot of regulation and public consensus on those pieces. So we can't make that into the chemical for the non, kind of food use or, other, chemical. This is how concept is about. And then this the long-term research, our zoologists have been working with us for 15 years. We're very much focused on Great Lakes, and we consider Great Lakes is a great resource for those biological matters. Actually, this species, we got a Chlorella, Sarraceniana, MSU. We do pay labor on our specific strains, and we selected 5 years of effort. We selected from of the Lake Michigan, and it's called adapt algal species. And even though Chlorella is everywhere, and any kind of water stream have this, but this is very unique. They can tolerate fairly low temperature. Still kind of at decent growth. And we build this facility and power plant and this fairly hassle process because everything is on the power plants on the Homeland Securities under EP's radar. So anything you take out from the chimney, you have to report and all those kind of, even though we just take a sleeves the out of the chimneys, carbon streams, but still actually recorded by the EPA. And these systems actually cubic meter systems in the 100 liter to cubic meter systems in our power plant. We generate quite a bit wet biomass because we need a certain amount of biomass to do follow up with feed animals and doing all those kind of stuff. So this is really long term. 2015 we started running after the pandemic, but we take 1 year's data. We all run all kinds of including microbiology research, and then all the biomass productivity, all the research on that, just data. Give it a bit summary in next part. So as mentioned, algal biomass we got from the flue gas on the water streams, pretty clean. So actually we feed chicken. So we run the full, because of fairly rich, nitrogen content in algal biomass, 56% of, the biomass is nitrogen. And we mix with the chicken meals. Actually, chicken love that because that fishy smells. If you look at the algae, no matter the freshwater algae, the seawater algae, they have this very unique fishy smells. And then the protein composition is very similar with egg and soybean. So this is a very good protein source. And particularly in Asia, like Japan, all those countries, China, it's quite a bit of seaweed is similar, the things with that. And for those algal biomass and growing on the waste streams, we cannot produce a food. So this is one of process. One of my colleagues in chemical engineering, the patent technologies, actually produce a polymer. And from the protein source to produce polyol, this is actually in the traditional chemical engineering process, 7 steps. The Dr. Nayaran's process only have 2, patent technology. So we turn this algal protein into the polyurethane. Actually, this is a car company is very interesting on that particular Ford, because Ford companies they start the talk about sustainability. They want to kind of the things they're using actually are sustainable. So they are very interested in this type of forms coming from of this carbon dioxide. This is literally they can claim and carbon dioxide based polyurethane. So we're still developing very much in the chemical engineering, and we'll give them the biomass. They develop all kinds of process, trying to develop like a hard form, soft form, those kind of stuff, but polyurethane based. And the next process is polyurethane is one. Another way is like we want to extract the M and the protein, turn them into this, the amino acid, salt solutions. And the reason we want to do that, I actually want to use those, solutions to replace the amine. Amine is actually current chemicals in the power industry, particularly in Florida. There's a couple of power plants using that to massively the absorb the carbon dioxide from the chimney. Very, very efficiency. Chemistry behind of that is kind of carbamate. Carbamate is chemical, can be under different pH ranges or different temperature. They take carbon dioxide, release carbon dioxide. So we want to use this algal-based amino acid, streams to kind of to replace. Amine is very toxic. It's carcinogenic, compounds. So you have to be very careful handle those kind of stuff. But this amino acid based the algal solutions very human friendly coming from the algae. So this is some of experiment we did and do all those kind of absorption using our flue gas and give you a little bit summary. And this is, the algal amino acid based salt solutions in terms of carbon capture. So we can capture 21 grams carbon dioxide per grams of dry algal biomass. You consider source of the amino acid production from algal biomass. Algal biomass alone is 0.88 grams because it's photosynthetic. This like algae, just like plants. They're photosynthetic. It's still very efficiency, but if you use industry standards, right, it's still pretty slow. So this is the kind of things. This is why we talk about system integration. Biological systems, chemical system together, right? We really can improve the efficiency. Everything's coming from the algae. You just need to do a little bit of processing, extract the components, turn them into some sort of chemical forms, can like a 20 times increase in terms of carbon dioxide efficiency or capture efficiency. So then the engineers, we want to see the big picture. So we can scale up to a 150 megawatt the power plant. See if you implement those type of technology, what we'll get at the end, how big the scale is going to be. And you think about this, the typical like 3,000 metric tons carbon dioxide production. And we still need quite a bit, space, 2,800 cubic meters reactors, almost like our, digester. You'll see our big digest size. Compared to like you need like 100 acre land for, algae cultivation. This is very, very small. And using such a small reactor systems combined with the algal, the amino acid salt capturing, actually we can develop systems, just jump to the next power plant to really kind of, sequester almost like a 90% of, carbon dioxide out of that. And once they reach the carbon dioxide, this give you a power plant another, products. is, the pure carbon dioxide. They can sell, they can do all those kind of things. Like current MSU, we have a couple of chemists working on plasma technologies, turning carbon dioxide into products, but they need a pure carbon dioxide. It's not like, this low concentration carbon dioxide. This is a little bit summary on that piece. I can share Emmy can share the slides with you guys, so you can distribute later on. So. And then again, this energy balance, you can see we compare with the MEA. MEA is an amine process, is already commercially being used in United States and the Europe. You can see this, the amino acid source solution. We really can reduce energy consumption by 50%. Then compared, put all those kind of carcinogenic and chemical handling aside, energy efficiency also is pretty high too. So that's kind of a two individual case. I really want to quickly go through some of the examples, the considering system integration at a pallet large scale level. It's not like in the bench or, so first one is the one that really kind of look at a system analysis for entire Europe's. It's pretty big effort, 3 years effort on the MSU working with our European colleagues, University of Bologna and a couple other institutions, UC Berkeley too. Berkeley's, economic development is part of that. We develop all those kind of model stuff. Second one is really solar power itself. This is a little bit on the advanced side, and we develop those kind of decentralized self-sustaining systems and really clean up the water. Third one is really farm-based EVs. Electric, I know the Maryland is pretty big. I know a lot of people in Maryland doesn't like, the renewable natural gas. They don't like the pipelines. I think in legislation body, I think I give a talk into Maryland's the legislation body probably next month. They asked me to give them talk regarding the RNG stuff. And this is the EVs, another pretty big piece. And the last one I want to show you a little bit our test bed concept of, very quick, it's just all the picture stuff. And then this is kind of European food, energy, water, Nexus solutions. We're developing energy, water connection. Good things like European unions collect all the data. So we have all the data to build this kind of model. We divide model into 4 parts. And particularly, this project is funded by Horizon, European, unions. Actually, start points is really kind of, this, Russian, Ukraine, the conflicts and the war stuff, so because Ukraine and Russians are two major the crop producing countries, and including Turkey. And we really want to see the impacts, those, the things on the entire Europe and in terms of entire global, food supply. So kind of dividing into this a lot of data. This a lot of, our, the European team did a great job. So put all those kind of numbers together. And we run all kinds of analysis, and we do the base scenarios, and based on current data, we consider each region we have the mean values and statistically generous numbers, and put that number on the ground. Let's find out all those energy, food, water scenarios, and we run this kind of chart. See this is the base case. The right line, and then any increase like about electricity, crop increase using the median values for each region, and South, North, and West and East Europes. And then this is some potential. Look at those numbers, not those numbers in terms of yield, those things already there. But for example, West Europe's and Germany doing very good jobs. We use the Germany as example to all those numbers. But other countries catching up. Again, similar condition with the Germany, like some of the northern Italy part of the France piece, we can do that. So this is just a little bit potential. And the mean values are almost like we believe we can achieve in a very short time period. And this potential needs some efforts because irrigation systems, water resource systems, even kind of energy production, you need to build some new power plants for this biomass utilization. And we did a very comprehensive GIS analysis trying to kind of map them up. Those kind of, the results. Actually, towards the end of for these papers, for this study, we believe European Union, if you look at each components, put, still the East Europe's, Ukraine, Russia is very important in terms of food in the global food production. And but if just consider European Union itself, so if you leave Ukraine and the Russians out of picture, out of the 3 components, right? They're still okay. However, there's some impact. This next level, they're still doing research for the global food chains. And the European Union is partly that okay, they can self-sustain other 3 regions, their food production, energy, and water. However, Russian and the Ukraine's, the food, the production will impact quite a bit, like Africa, those kind of, continent. That's the next steps. So then back to, the United States. So we developed this, solar powered, really container based and decentralized. We can put, electric, the system. We need simple. And I'll build this container and we work with Panasonic using their advanced, the latest, solar panel to do that. Right now, this solar panel, we have 22% efficiency. It's very, very high. And typical, solar panel, we're looking at 15 to 18, something like that. This research units, we have pretty high, efficiency. Then we treat the water. You can see this is we are focused on high strength. We're not interested in those gray water type of thing. We're interested in black water because black water is very hard to treat. Black water means the latrine water and some kitchen water stuff. So you can see this during this process we can get a clean water. This clean water actually satisfies EPA's discharging standard. But we want to further develop, to kind of get into some recycle purpose, can use for the laundry or some other things. And but you can see the energy outputs. We really want to achieve energy neutral and also water cleanup. This is one of the systems. Our dream is like a subdivision down the road in the United States. We can put those things in that subdivision to clean up the water, really address current infrastructure issues. If you look at our wastewater treatment systems, right? 80% of the pipeline, less or more leaking. And this kind of aging stuff. You don't want to invest another couple $1 trillion to do those kind of stuff. You need to put in new technologies. Decentralized system, I'm not saying that's the only solution. Could put into the picture and at least as part of the solution to alleviate some of and really advanced technology next levels. So then back to the EV stuff. Everybody knows those, the clean gas, the biogas used for heat electricity has been a long time. And right now, of course, RNG with all those compliance market rings and the California low carbon fuel standards, everybody moving in this direction. However, for the small, medium farms, as I mentioned earlier, they do not have that, capacity to do all those, the large amount of production. We need to figure out ways to help them. This EV could be a solution for them. Of course, right now it's pretty slow because of all the e-ring stuff. And what we did is the governor's project, and she is very interested in this renewable energy stuff. And 3 years ago, she found this project. We do work with Detroit-based this Bollinger. It's a EV SUV actually for agriculture use. Very fancy, and the vehicle is pretty cool vehicle actually. And they can put all those corn store in the middle of the truck, travel around. We do have our own so we build our own tractors, electric tractors. This is hot systems on a trailer. And we do work with the engine company. Those engines can directly burn on those, the natural, the renewable, no, not natural biogas, dirty biogas. You can see the gas bag there. So we demonstrate quite a bit this summer on the West Coast with our west, side of Michigan. We demonstrate that. Really, this is for one cattle equivalent waste. You generate electricity. I drive a Tesla. I can kind of, power my Tesla 10 miles per day. So good enough for me back and forth between work so you really want to showcase, say, okay, this is the thing, it works, it can do the thing. We really need to put the economic and other component on the top. Okay, last piece. I have a few minutes, and kind of just go through this, climate smart animal agriculture testbed facilities, a newer facility we just finished last month. And the dairy in the front end and the back end, we're still doing this, back end upgrading is finished by next year's. The front end, $75 million, the project is a very big project and quite expensive because research component. 650 cow dairy farms really don't need that much money, but it's AI driven and optic fiber because vet schools on board. And vet doctors wants, to monitor the system 24/7. Actually, they want a camera 4K or 8K and streams and on individual cattle actually 24/7. So we build those kind of things based on those requirements, and then we do work with IBM. IBM's take this as their example for called customized generative AI. So the develop AI solutions for rural community. They want to take that as this is why I mentioned testbed. Testbed is not only for animal research, for end research. There's much bigger scope. Even kind of considering currently we're doing this data center research too, using that facility because if you look at data center stuff here everywhere, and Michigan needs in the short term years we need 3 times the electricity to power all those the atomic vehicles their demand on those cars, so the FSD, all those kind of stuff. It's huge. It's not we're not going to be building, the power plants to satisfy this 3 times the electricity demand. We need some other ways to do that. Agriculture, as mentioned earlier, could contribute and could provide quick solutions to satisfy some of the demand. I'm not saying all of the demand. So this is our facility on Southern Campus. For some of you visit MSU, give tour you around. And it's 165,000 square foot, the building, single building. The reason we build single buildings, we want to do research on that, climate control and emission control. And all those fans in there, so all on the VFD, individual control there, we can really kind of control every single fans, their speed, and to manage the emission inside of the feedlot and temperature profile, all those kind of stuff. Actually, BASFs right now, so we are trying to work together. They have some very cool technology. They can take small trace amount of the methane in the atmosphere as a feedlot and turn them into carbon dioxide, simply reduce the emission from feedlot. So it's a big feedlot, and we do have robots, 2 robots. Robots milking machine is pretty popular, but we have both the robot milking and the traditional parlor, and trying to do the really on the same location, do the side-by-side comparison. And that has those standing stations for the surgery, all those things in the location. And then again, the feed study, right, like Elenka and Cargill, we are been working together. They want to use those kind of auto feeder to really study this nutrition's impact on the animal, the milk production and also emission stuff. And this typical, freestyle and parlor and this milking parlor. And yeah, then anybody coming in next coming months, give me a call. I can tour you these facilities. And the back end is our manure building and the digest on this corner. So this is finished. Animal moving the July 17th. Right now it's been running almost like 2 months. And we still a lot of things we're debugging and, facility like that, water issue, all those things we're still working on. And this next part is ongoing, another $25 million upgrading for our digestion systems and really put the RNG on the top of that. So this kind of, some of, the things we're doing right now, and it'll be finished by next year. And I just want to give you a little bit of perspective. This is AI generated. If you look at the figure, this is a ChatGPT 5 generating the figure. I gave a couple of numbers, but those numbers are calculation. I just want to kind of entire audience of our colleagues in University the Marlin just jump out of the box. Think about it, we're working on agriculture, what we can do, and for all those things. Just this example for the methane production, and look at the entire country. This is how much the methane and we can generate. And then if you look at it, on the other end, like 2 weeks ago, the SpaceX did a great job, send the starships, to the kind of 10th flight, right? And if you look at the starships, all those, the rocket around the world, all the methane driven. Actually, thanks to the SpaceX, they start methane case. So if you just look at the U.S. animal agriculture, we can power at least in near future, if you talk about the Mars trips, right? More than 5,000 trips per year. It's more than enough methane to power entire U.S. space programs. So down the road for even kind of, to the moon, to those places. That's why numbers. I always show students, you just need to sometimes jump out of the box, look at the big picture, right? And the semi-truck, and 50% of our semi-truck on the road can be powered by our agriculture, animal agriculture. And then other things like chemical production, greenhouse gas emissions. So you can see this, just want to show, the audience, how big the agriculture is going to be. And it's really not only just our food, our fiber, our clothes, wells. It really can make this global much healthy and much, more sustainable. So with that being said, yeah, this kind of, sorry, a few minutes, probably this collaborator, I've not put all the names there, our colleagues around the world, and then all the funding agencies. Okay, thank you all. Sorry, take a little bit longer, only a few minutes left, so.